this video, I will be enumerating all 46,972 prime knots with 14 crossings. And I know what you're thinking. How many composite knots are there of 14 crossings?
Ah, darn it. There's no way I'll get this knot untied.
Oh, hello, Penguin. What's the matter?
I bet my friend 25 grand that I could untie this knot, but I can't do it.
Well, that's unfortunate. That's a trefoil knot you've got there, and it's impossible to untie it.
You're making it up. Prove it.
I was hoping you'd say that. I guess I won't be enumerating all those prime knots after all.
Thank God.
First, let's get some terminology straight. Knot theory is a branch of topology in which a knot is defined as a string that forms a closed loop. If it just forms a regular loop without crossing over itself, we call this an unknot, because, well, it's hardly even a knot. In other words, an unknot is a knot which has a projection with 0 crossings. A projection, also called a diagram, of a knot simply means to take that real 3-dimensional knot and smash it into a 2-dimensional plane. Now the number of crossings in a projection is just the number of times the knot crosses over itself for that specific projection. The thing is though, different projections of the same knot can have different numbers of crossings. For example, these are both the unknot, but the first has 0 crossings and the second has 1 crossing. We say they're both the same knot since we can untangle one into the other without ever letting the string pass through itself.
That means that my knot could be the unknot. I just need to find the right way to untangle it.
Well, let's think about that. Kurt Meister proved that any kind of untangling motion on knots could be described using a sequence of moves known as Meister moves. There are only 3 Meister moves: twisting, moving one string over or under another string, and moving one string over or under a crossing. In topology, you may hear the term ambient isotopy. This just refers to a continuous distortion of space, which in real life would look like grabbing a knot and moving it into a different configuration without breaking it. So if you take a knot, then ambiently isotope it into a different configuration, you can end up with 2 different diagrams of the same knot. Meister moves allow us to transform the first diagram into the second one, since we know that they came from the same knot. And just with these 3 moves, we can transform one projection of a knot into any other projection of that same knot. This means if it's possible to untangle the trefoil knot, we'll be able to transform it into an unknot using only the 3 Meister moves. But there's still a problem. What if we keep trying Meister moves, but we can never untangle the trefoil knot? That doesn't mean it's impossible, it just means we can't find a way to do it. So, how could we actually go about proving that it's impossible? Any ideas?
We could give up.
Or we could use an invariant of knot diagrams called tricolorability. Consider some knot. It is tricolorable if and only if we can color all of the strands using at least 2 colors, such that at each crossing, the 3 strands are all the same color or all different colors. And when I say strand, I just mean each individual segment of the string in the knot diagram. So look at the trefoil knot, for example. It is tricolorable since we've managed to color all of its strands using at least 2 colors, and at each crossing, the 3 strands are 3 different colors. And of course, the unknot is not tricolorable, since it can't even meet the first condition of being colored with 2 colors, since there's only 1 strand. So this is pretty cool, I guess, but what's the point of determining whether or not a knot is tricolorable? Well, tricolorability has the super useful property that is invariant under the Meister moves. What this means is that if some projection of a knot is tricolorable, then after we perform any number of Meister moves on that projection, it will still be tricolorable afterwards. And likewise, if a knot diagram is not tricolorable, then it still won't be after Meister moves are performed on it. Proving this invariance is just a matter of looking at each individual Meister move. If we take a knot which is already tricolored, then zoom in on a small section and perform a Meister move on it, you will see that it's possible to color each strand in our small bubble in such a way that each crossing has either 3 colors or 1 color. We don't necessarily have to use 2 colors in each bubble, since we're assuming the knot is already tricolored, so we know we've already used at least 2 colors somewhere else. And importantly, we haven't changed the color of the outgoing strands, so we know that we didn't mess up the rest of the knot, which is already tricolored with these colors of strands. And you can make a similar argument for knots that are unable to be tricolored. This means that if one knot is tricolorable and another one isn't, there's no chance they can be the same knot, since tricolorability is invariant under the Meister moves. So, I hate to say it, but since your trefoil knot is tricolorable, there's no chance you're going to be able to untangle it into the unknot, since the unknot is not tricolorable.
Oh well, I always say that learning a new proof is worth losing $25,000.
I sometimes say that too.